Greetings, everyone. My name is Sanyukta Agarwal, and I was a surf intern with the NuSTAR lab. The summer, this summer, I worked on exploring the innermost regions of an accreting black hole using quasi-periodic oscillation. So here we have the electromagnetic spectrum and the X-ray range we can see lies from around 100 electron volt to 100 kilo electron volt. And the Nuclear Spectroscopic Telescope Array, the NuSTAR, is a focused satellite that observes in the 3 to 79 kilo electron volt energy range, which is the hard X-ray energy range. And whereas satellites like Chandra and Exynom Newton observe in the 0.1 to 10 kilo electron volt range, which is a softer X-ray energy range. So now let's come to our sources. Our sources of interest are X-ray binaries, which are a class of binary systems that are luminous in X-rays. Here we can see a compact object, which is the primary, an accretor, which usually consists of any compact object like a black hole or a neutron star. And here we have its companion binary, which is mostly a main sequence stars. So the accretor attracts mass of the companion and the mass rotates and forms an accretion disk. And here we can see the accretion disk as the mass from the companion falls into the accretor. Okay, now we come to our particular interest in black hole X-ray binary. So when an X-ray binary has a compact object as a black hole, we call it a black hole X-ray binary. Now, most black hole X-ray binaries are transient in nature and spend most of their time in a quiescent state, where the accretion rate is low, and so are the flux counts. So here we can see on the right figure at the bottom is the quiescent state, where the disk is truncated at a large radius, and most of the dots we can see are advection-dominated accretion flow. So as the accretion rate increases, the black hole X-ray binaries are said to go into a outburst, and the flux starts increasing along with it, and the source goes through various spectral states, as you can see on both the figures. It goes from a low hard state into an intermediate state, and then to a high state. And then it returns from the high soft state, going through the soft and the hard intermediate states again, back to the low hard state, and then to a quiescent state. And that's the whole outburst. So as it goes through different transitions, it forms a Q shape in the hardness intensity diagram, or the HID. Here on the left, we have the HID, where you can see hardness on the x-axis and luminosity on the y-axis. So as it goes through from a low state to a high state, the disk gets closer to the compact object, and we see a decrease in advection dominated accretion flow, or ADF. So these dots represent ADF, and the horizontal lines represent the disk. So another interesting feature which is present in which is seen to be present in BHXBs are QPOs. So QPOs are quasi-periodic oscillations which result when hot gas piles up near the inner disk region of the black hole, and it radiates an X-rays with an intensity which varies and repeats in a particular pattern, and a nearly regular pattern. And that is, it flickers about a certain frequency. These signals come from a non-thermal emission, and thus making it optimal to be studied with the hard X-ray band which NuSTAR observes in. So now we come to a particular source of interest. Our source of interest is called MAXI J1803-298, and it was first seen to go into outbursts using the MAXI Sky Survey on the International Space Station by Cerrone in 2021. So NuSTAR had 4 observations on the outbursts of the particular source. Here are the 4 lines you can see of the 4 outbursts. So the green one seems to be in a hard intermediate state. The red one seems to be in a soft intermediate or soft state. Same for the yellow one, which seems to be in a soft intermediate or soft state. And the pink one again seems to be in a hard intermediate state on its way back. Since most of the QPOs are found in either the intermediate states or in the beginning of the hard state, so we chose to examine the green line, which where is the source transitioning from the low hard state to a high soft state. And the light curve I've plotted is using data observed by MAXI. And below is there's a hardness ratio where I have taken counts in the 4 to 10 keV range and divided by the counts in the 2 to 4 keV range to get the hardness ratio. So you can see as it starts in hard spectral states and it slowly transitions to a softer state. And then it should ideally be transitioning back to the hard state, but MAXI does not seem to have enough data points. Next, we come to the light curve. So on my right, I have the light curve of the particular observation I'm using. So as NuSTAR rotates about the Earth, we can see 11 different orbits out here. Now, one of the interesting features we see here are dips in the light curve. So we see there's a dip in the first orbit where the intensity seem to be increasing. Then second, third, and fourth seem to be consistent. Whereas there's again a dip in the fifth one. 9, 6, 7th, 8th are consistent, and 9, 10th show dips, and why 11th is again consistent. So we decided to check upon the hardness ratio and how are the spectral states over there. So we saw that HR1 and HR2, as explained, HR1 in 6 to 10 by 3 to 6 keV, and HR2 in 10 to 79 by 6 to 10 keV, show increase in hardness as the orbits have dips. So there's some correlation between the spectral state or the hardness state of the source and the dipping or increase or decrease in the intensity. Now we come to analyzing QPOs. So QPOs is analyzed using power density spectra or periodograms of the source, where we look at the frequency domain. So NuSTAR was mostly designed to look at the spectra and do spectral analysis, and thus has a long and a variable dead time of 2.5 millisecond per event. And thus it caused distortion in white noise levels when we look at the PDS. So here you can see a non-corrected or like a PDS if you extract from NuSTAR data. And here you can see in the left, there's a dip in the white noise level and it goes back up, which is not usual. It's unexpected. So to solve this issue, what we do is we use Fourier amplitudes. So NuSTAR has two different detectors, independent detectors, FMA and FPMA and FPMB. And we use observations from both these detectors independently, and then we use the Fourier amplitudes from both of these, and thus we can filter out the distortion. And thus, after the FAD correction, we find this very normal expected white noise level on my right hand side. And the peaks we can see here are the QPO frequency or the QPO peaks. So these peaks are correspond to the frequency at which our QPO is found. And then the small kind of bumps you can see around 1 Hertz are called subharmonic. So we look at detailed periodograms or PDS of every orbit, and we also look at them in different energy ranges. So here I have calculated the PDS, FAD corrected PDS for all the 11 orbits. And here you can see that there are some differences across each orbit in the PDS. May it be in the frequency, may it be in the subharmonics, and I've written them with Lorentzians because PDS, the QPOs are expected to be following a Lorentzian shape. Next, I have divided all the orbits into a set of trees, and I've brought them together to see evolution across a short time scales. So as we can see, first orbit is a dip, one, second and third are not. And here you can see slight variation in the QPO frequency as it moves forward. And there's slight variation in the subharmonics too. We also notice a variation in the power level in the lower frequencies of 0.01 hertz around. Then below we have 4, 5, and 6. And again, we see a similar variation and a movement of the QPO frequency. Same for 7, 8, 9, and 10, 11. So now we decided to look at, okay, we saw short time scale evolution. Now we wanted to compare if there's any difference between all the dip ones on my right and all the non-dip orbits on my left. Here we can see the normal variation as we saw that from 2nd to 11th, as the graph goes from blue to green, there's a movement of the QPO frequency. The power level seems to change, but overall they seem jumbled up. And there's also movement of the subharmonics. And as you can see, the subharmonics seem to decrease in power as we go ahead in time in orbits. Now we look at the non-dip, like the dip orbits, and we see a similar variation that the QPO frequency moves forward with evolution in time, and so does the subharmonic, and there seems to be a slight decrease in the power level of the subharmonic. So here I've plotted all the orbits together, all the orbits PDS together, and you can see a clear movement in the QPOs. But there doesn't seem to be much difference between dip orbits and non-dip orbits, suggesting that QPOs are not correlated with the dips we see in the light curves. Here I have taken the full light curve of our observation and divided into 3 different energy bands, the soft, medium, and hard, corresponding to 3 to 6 kV, 6 to 10 kV, and 10 to 79 kV respectively. So we see the soft band having the highest power, followed by medium and hard, where hard is the lowest in power. And we also see the subharmonics varying. The soft one shows a really strong, relatively strong subharmonic compared to the medium and the hard one. So this shows that there might be relations between the QPOs and the energy band in which we might find them. So this is the Lorentzian fits for the full light curve in soft, medium, and hard band. So overall, I found the QPO frequency for the full PDS to lie around 0.4 hertz. And across various orbits, it seems to evolve from 0.4 hertz to 0.5 hertz. I have performed these fittings using multiple Lorentzians on Stingray. And on the top panel, you have a semi-log plot, and on the bottom panel, you have the log-log plot. A problem with Stingray is that the error values it provides for these fits are really high than what it should be. So that's one of the problems I faced while performing or trying to find the QPO frequencies. So large error bars and parameters of Stingray model fits. So one of the possible solutions we can think of is trying fitting with XSpec. So the future plan for the project is fitting all the PDS in XSpec. And I also plan to check the root mean square or the RMS of the QPO as a function of energy. As we saw in the full LC across different bands, there was a difference in the power with different energy bands, and we saw a difference in subharmonic too. Then I also plan to check the evolution of photon index by using spectral fittings using XSpec, because we saw the dips corresponded to an increase in hardness. And then I also plan to determine the type of QPO, whether it's a type A QPO, type B QPO, or type C QPO. And that will be best done using the statistics from XSpec. Here are the references, and I would like to thank my mentors for helping me out and guiding me throughout. Thank you.